Now here I have an example where we apply a voltmeter to a voltage source that supplies some current to a resistor. So the resistor is the load. Here we have the voltage source, and we want to measure the voltage across the resistance. Now, when you look at the voltage source here, you will see that I do not only have the voltage source symbol, I also have a series resistance. And now think about last time when we discussed the example where we connected two lamps in parallel to one battery. We said that ideally, when we connect the second lamp in parallel to the first one, the brightness of the first one should not change. But in reality, and I mentioned that too, in reality, you will see probably that the first lamp is a little bit dim. The brightness won't be the same anymore. And the reason is that the voltage source is never an ideal voltage source. A real voltage source has a series resistance, an inner resistance. And when we connect something outside here and increase the total current, we will increase the voltage across the inner resistance. And according to Kirchhoff's voltage law, the external voltage will drop. It may not be much, but the effect is there always. And this is exactly what happens when we connect the voltmeter in parallel to this load. Because in the real voltmeter, there is this inner resistance, RIV, and there will, of course, be a current flowing through that resistance. And this current now flows through the inner resistance of the voltage source, and the voltage that we want to measure will drop. So once we connect the voltmeter, the voltage is not the same anymore. It changes. We basically make a mistake. It's not the same circuit anymore. So think about this. What is the requirement, consequently, on this inner resistance? Two possibilities. Should it be small or large?
It should be large, so that way the original resistor takes the lion's share of the current.
Exactly. This inner resistance must be as large as possible, or should be as large as possible. Because when it's large, for a given voltage, the current that's flowing here will be small. And a small current compared to the one which flows through the load anyways. So the ratio is important. A small current flowing here, this will not change much. So this effect will probably be irrelevant, negligible. If this inner resistance were small, maybe in the same range as our load resistance, then basically we would add the same amount of current here as we already see here in the load. And this would definitely change a lot. So that's the reason why the inner resistance of voltmeters must be large. And as I said, typical values are in the range of megohms, 10 to 11 for this type of device. You cannot make the resistance infinitely large, because as I said before, the current will be so small that it will become very noise prone. So you will probably not be able to measure anything anymore when you do that. So there is a limit. It's always a compromise. Okay, so this is the voltmeter, voltage measurements. We now know how a voltmeter, a digital voltmeter, looks like internally and what the effect can be when we connect it to the circuit. Now let's look at current measurements. How do we measure a current? And what I'm showing here is again the example where I connect a lamp to a battery. A current measurement is like measuring the flow of water into your house, for instance. So the water has to flow through the measuring instrument that you use there. And it's the same for current measurements. The current that you want to measure has to flow through the instrument. So we have to connect it to the circuit such that the current, in this case, the current that flows through the lamp, it comes from the voltage source and flows through the lamp. It has to flow into the instrument. And we have to choose, or we can choose, I'm showing this in the camera, we have to choose one of these two connectors here. They are for current measurements. The current flows in, comes out of the COM connector, and then back to the voltage source. So we have to connect the ammeter. This is called an ammeter. This is the common symbol, the standard symbol. We have to connect the ammeter in series to the lamp in that case, not in parallel. If we would connect it in parallel, well, there would be some current flow through the ammeter. That's not what we want to measure. Some other current is flowing through the lamp and the instrument doesn't see it. So it doesn't make any sense to do that. It has to be connected in series. It doesn't matter whether you measure it here, upstream of the lamp, or whether you measure it here, downstream. The current is the same everywhere in this loop. Before we connect the lamp, the electrons are present everywhere in these wires and devices. When we connect the voltage source, all these electrons that are present along these wires are just moving at the same time. Nothing is lost, no charges are lost inside the lamp so that we see less on this side compared to that one. It's the same everywhere in the loop. So you can measure it here or you can measure it here. Doesn't matter. Now, what happens inside the multimeter when we configure it as the ammeter? And again, my question will be, what do we have to take into account? And how does the instrument maybe change our circuit? What can be the impact on the measurement of circuit behavior? Now, okay, we have the two connectors again, one up here, and this is the COM connector, the negative side. We have to make sure that the current that we want to measure, this is the current I, flows into the one connector, and there's usually a fuse in order to protect the instrument against too high currents. The current flows in and then flows through some resistance, and you can see there's again a resistor bank. Let's call it the resistor bank. They are not connected in series. They are now connected in parallel. But it's configurable. We have switches. So we can either connect only one resistor into the current path, or we can connect additional resistances in parallel. Now, what is the purpose of this resistance? Why does it have to be there? Well, this part of the instrument is the same as before. We have a display, we have a microcontroller, we have an analog to digital converter. And this analog to digital converter is always measuring voltages. This does not change. Even if we measure currents externally, the A to D converter can only measure voltages. So we have to convert the current into a voltage. How do we do that? Well, let the current I pass through a resistor, for example, R2, and you will get a voltage across R2. And this voltage is now connected to the A to D converter. Okay, at the end of the day, on the display, we want to see a current value. So what is the current now? Okay, the position of the switch is known by the instrument. It's known. The microcontroller knows what the position of the switch is. So the microcontroller knows what the resistance currently is. Well, and the microcontroller can calculate Ohm's law. I is the voltage divided by the resistance. And then this calculated value is displayed. So this is how it works. And now, why do we have all these resistances in parallel and the switches so that we can configure it? Well, that's the same idea as before. If the current I that we want to measure is very large, then we need to use a small resistance, a small total resistance. But the voltage connected to the A to D converter does not exceed the limits. But if the current is very small, using a very small total resistance would result in a very small voltage here, and the accuracy degrades again. So that's the reason why we make this configurable. If we connect only one resistance, we have the maximum, basically, the maximum resistance. When we connect additional resistances in parallel, and we discussed that last time, the total resistance will be reduced. Okay? Good. Now you know how it works. Now let's see how this may change our circuit. Well, when we connect a real ammeter in series with a load, in this case here, in this example, it's again a load resistance, we will basically connect the internal resistance of the ammeter in series with our load R. In total, we will now have R plus RIA. RIA is the total inner resistance of the ammeter. So we add resistance into the current path. And of course, this changes the current. The voltage stays the same. We add resistance, current goes down. So we are in fact not measuring the current anymore that we want to measure. But if we do it right, it may not really be a serious mistake that we do. But what is the requirement on this inner resistance of an ammeter? Again, two possibilities. Large or small? Well, should be as small as possible. Within the limits that I explained before, if you make it too small, the voltage may become too small. You can't measure it accurately anymore. Okay, but in general, it should be as small as possible.